Hi, we're Team sklearn2 and this video will give you guys an in-depth overview of our Pacman agents. Our team consists of two AI techniques, A-star heuristic search and reinforcement learning. Both of our offensive and defensive agents utilize these techniques. We use A-star heuristic search as a tool to get our Pacman to certain areas of the grid. With the addition of a heuristic, our Pacman was given a brain. This meant that our agents would also take into consideration of its surroundings when getting to a position on the map. With that in mind, we use A-star to navigate our agents to the safest path home and pathing to the nearest anchor points, which will be discussed later in the video. We also use reinforcement learning, specifically approximate Q-learning. We train the agents over many episodes and provide features for both the offensive and defensive agents. Due to the time constraints, we constructed very specific features such as the distance to the anchor points, the distance to the recently lost food, or the distance to the nearest capsule to reduce the training time for our agents. These numbers are used to form a linear approximation which outputs the best Q values for the state action pair. But most importantly, it is the reward function that makes or breaks the performance of our agent. This brings us to the next part of our video, the reward function. What did we consider when we constructed our reward function? There were many things that we had to consider when we constructed our reward function. After many hours of consulting with the staff team, we were advised to reward often. This means if the agent made a mistake, such as dying or entering the enemy territory for no known reason, then we should heavily punish the agent. Alternatively, if the agents were able to make their way towards the food and return them home successfully, or killing the enemy agents, then we would give the agents a good reward. There were limitations to both A-star heuristic search and approximate Q-learning. In some cases of our A-star heuristic search, sometimes it would take too long to reach a goal state, and hence our agents would crash. This will be discussed further on later in the video. As for reinforcement learning, to be able to train our agents, we needed resources to train our agents against. Initially, training agents against the baseline team was good, but as our agents got smarter, the training became redundant. Hence, to counteract this, for the final submission, we trained our agents against our agents from the preliminary submission.
Now I'm going to talk about the design and the strategy that the team came up with. So before the preliminary contest, the team has decided to go for one offense and one defense strategy. So an advantage for that is it's very simple to implement, so the team can just focus on one agent at a time instead of having to worry about combining the two agents. Given the case that it was before the preliminary contest, but the deadline was very tight. In order to guarantee that both the offensive agent and the defensive agent perform well, we spent a lot of time working on the Bayesian inference for the enemy prediction to make sure that both agents has an advantage of knowing where the enemy are on the map. Moreover, our defensive agent also have the ability of using the recently lost food in order to get a more accurate estimation of the enemy location. So this strategy actually placed Earth in the 8th place, just right below the starting top for the preliminary contest. By observing the agent, we actually noticed some of the limitation of it. So the first thing that we noticed is an increase in the complexity of our offensive agent. In the case where heuristic function becomes more and more complicated, it actually slows down the computation time of offensive agent significantly. Secondly is the problem in the strategy itself. Having the two agents working separately might be easier to implement, but it actually makes it less efficient in both defending and attacking. So as a result, we came up with a hybrid tactic which combine both attack and defense in the same time. So in order to do this, we implement reinforcement learning on both of our agents and only use A-star as a tool to guide our agent to its goal. So in particular, our agent now can work together and it has the ability to decide to defense or attack when it needs to. In order to make two agents to be more responsive to each other, we also implemented a shared intelligence between the two agents. So the two agents now can assign what food one should eat, which anchor one should defense, to work together more efficient. As a result, we will always place top 5 for the last submission.
Now, let's dive a little deeper into the mechanics we used in order to enhance our features. The two main mechanics we used consisted of a prediction system, built off Bayesian inference. The second being a dead-end system, used to calculate dead ends at the start of every game. Let's have a look at our dead-end system. We used a maze-solving algorithm, called the wall follow algorithm, combined with the right-hand rule in order to scan along walls and find entrances and exits for our agent. In Tangent, we also incorporated a move counter, checking positions on the map with only 3 moves, including stop. By layering these two together, we are able to obtain something that looks like this. The yellow squares represent the dead ends. We used 2 algorithms and laid them on top of each other to provide our agents with information on whether the agent was in a tunnel, room, or dead end. Transitioning to our inference system, for situations where the enemy cannot be seen, Rather than giving our agent no information at all, we provide our agents with an inference of where the enemy could possibly be. The inference system lays two algorithms on top of each other, the first being the possible move layer. This layer stems from the enemy's last seen position and elapses tiles based on how many moves the enemy has gone missing for. The second layer is a noisy distance layer. This layer acts like a heat map. The more an enemy moves, the noisier that area of the map gets. Hence, the squares and positions around that area are increased in probability. By overlapping these two layers, we are able to obtain probability distribution across the map for our agent. Overall, we have been able to create two fairly smart agents based off A-star and Q-learning. Through Pacman, we have been able to observe the weaknesses and strengths of both techniques stemming from the main restriction of time. In the future, if we were to improve our agent, we will compare more than a couple of feature sets shown over many more iterations and episodes than we had done in this project. This is to observe a wider variety of behaviors and obtain the best one. In our case, with time against our side, we had to guide our agents with manipulated features in order to get the quality of agent we have today.